Welcome to solverfy.
Question 104 is very similar to question 103. It is a complex ion formation question where, knowing the equilibrium for the formation of the complex ion, the cobalt with 4 hydroxides, we should be able to solve, and the Kf value for the formation of that complex ion, we should be able to, once equilibrium has been reached, solve for the final cobalt concentration, the final hydroxide concentration, and the final complex ion concentration. We'll do what we did similar to question 103. Let's first identify the equilibrium that creates the complex ion with its corresponding Kf expression and Kf value. We have cobalt 2+ reacting with 4 hydroxides, producing the complex ion of cobalt with 4 hydroxides and a total 2- charge. The Kf expression is going to be the product concentration minus the reactant divided by the reactant concentrations, which is what we have here, product concentration divided by the reactant concentrations, each raised to their corresponding coefficient. So the only one that has something other than 1 is hydroxide, which is raised to the 4th power. And that Kf value was given to us at 5 times 10 to the 9. We can solve for the cobalt concentration once equilibrium has been established by first determining the concentration of cobalt before equilibrium has been established by recognizing we added 2.4 grams of cobalt 2 nitrate. If we take the mass of cobalt 2 nitrate, divide by the molar mass of cobalt 2 nitrate, this will give us the moles of cobalt 2 nitrate that we have in solution before equilibrium is established. We divide by the volume of the solution, which was given to us at 0.35 liters. This will be the molarity of cobalt 2+ before equilibrium has been reached. Once equilibrium has been reached and we form the product, then cobalt 2+ will be consumed by a certain amount we will call X. So we have minus X here. If I finish the calculation as much as I can, the cobalt concentration will be equal to this number, 0.03748 minus X. Now let's look at the hydroxide concentration. The hydroxide concentration will be equal to the amount that we started with. We start with a potassium hydroxide solution at a concentration of 0.22 molar. So this is the initial concentration of hydroxide. I will then subtract off the change that occurs when the hydroxide is consumed in order to make the product. If this is changing by X, then because this coefficient is 4, the change in hydroxide will be 4X. Then I can calculate the concentration of my product at equilibrium. If this decreases by X, this decreases by 4X, then this will increase by X, just looking at the coefficients. So I'll define my concentration of the complex ion at equilibrium as X. Now I'll make the assumption, because we have a large equilibrium constant, that essentially all of the cobalt is going to be consumed because we have a much higher concentration of hydroxide. The hydroxide will be left over in excess. If all of the cobalt is consumed, then whatever cobalt concentration I start with, it will now become essentially 0, and all the cobalt will be tied up in this complex ion, and the complex ion concentration, once equilibrium has been established, will be equal to the initial concentration of cobalt. The initial concentration of cobalt was 0.03748, so after equilibrium I will assume that that is X, and this is now the final concentration of the complex ion. Then I can solve for the hydroxide concentration, recognizing that it will be equal to its initial concentration minus 4X, or in this case 0.0701 molar. Now if I use this equation to solve for my cobalt concentration. Once equilibrium has been established, I will get 0, but I can't have it be 0, because if it were 0 here, then this would be undefined. So it needs to have some numerical value, which I can now calculate, knowing the equilibrium concentration of my complex ion, this value, the hydroxide concentration at equilibrium, this value, and my Kf, which was given to me. So if I rearrange this expression, my cobalt concentration will be simply equal to the complex ion concentration divided by Kf, hydroxide raised to the 4th power. I plug in these concentrations that I calculated and the Kf value provided, and I can solve for my cobalt 2+ concentration, which will be equal to, at equilibrium, 3.1 times 10 to the negative 7. So these then become the equilibrium concentrations for the 3 species requested.